Hello, everyone, and welcome to today's presentation, Government of Alberta Wetland Inventory Pilot Results. The ABMI respectfully acknowledges that our work takes place on the territories of Treaties 4, 6, 7, 8, 10, the Blackfoot Confederacy, and the Métis homeland, traditional and ancestral lands of First Nations and Métis peoples, whose histories, languages, and cultures are directly linked to the biodiversity that we monitor. We acknowledge and honor the traditional teachings of the lands that we work on and benefit from, and that reciprocal, meaningful, and respectful relationships with Indigenous peoples make our work possible. We are deeply grateful for their stewardship of these lands, and we are committed to supporting Indigenous-led monitoring programs while increasing our learning and understanding of Indigenous ways of knowing, being, and doing. And now a bit about our presenter today. Dr. Michael Merchant is a senior Earth observation data scientist in the ABMI's Geospatial Center and Earth Observation Insights Unit. He specializes in the development of AI and machine learning models, particularly those built on Earth observation and satellite remote sensing data. His work focuses on advancing diverse geospatial products and analytics that support biodiversity mapping, environmental monitoring, and data-driven conservation prioritization. Take it away, Michael.
Okay, thank you for that introduction, Sonia. Appreciate it. And hello and good afternoon, everyone. I'm quite excited to be here today to give this presentation that reports on the results of the Government of Alberta Wetland Inventory Pilot Project. So the project that I'll be talking today focused on developing methods for enhanced wetland mapping in Alberta, with a particular focus on meeting the provincial minimum standards for wetland inventory development by use of artificial intelligence, or AI, and satellite Earth observation techniques. Before I begin my presentation, I'd like to share just a few acknowledgements. First is I'd like to thank the collective project teams at the GOA, so Government of Alberta, DUC, Ducks and Land Canada, and the ABMI. This work that we did was completed in partnership between all of our organizations. Secondly, though, I would also like to thank the GOA for funding this work through the Wetland Replacement Fund. And I'd also like to acknowledge that the work was completed by the GOA through contracting DUC and subcontracting the ABMI. And lastly, I'd like to acknowledge that the technical collaboration between DUC and ABMI that was guided by our MOU that outlines our shared interests in wetland ecosystems, wetland science, and wetland mapping. And as you can see here, our project membership teams were quite large, consisting of many individuals. So a big thank you to everyone from the GOA, DUC, and ABMI who contribute to this project and who made the success of this work possible. So that included, in particular, the GOA Environment and Protected Areas project team who oversaw the mapping work, and the technical and management teams from the ABMI and DUC. So thank you to everyone who was part of this project. And with that, let's dive into a bit of a background on wetland mapping in Alberta so that I can provide some context on the pilots that made up this project and the work that we did. So wetland inventories are quite critical for understanding, managing, and protecting aquatic ecosystems. And they're especially important in Canada, where wetlands are quite widespread and play a key role in, for example, national biodiversity and climate objectives. And for example, in Alberta, wetlands are very extensive. So nearly 30% of the province is estimated to be wetland covered, according to the current provincial inventory, with wetland coverage being highest in the northern boreal regions and lower in the southern prairie regions. But when we have accurate wetland inventories in place, they can help us support ecosystem conservation, watershed modeling, long-term trends monitoring, and also inform things like wetland protection, restoration, land use planning, and even policy implementation. And in the province of Alberta, reporting and management of wetlands currently relies on the Alberta Merged Wetland Inventory, or the AMWI. And despite its usefulness and novelty at the time of production, this inventory does have several notable limitations. So for example, it has limited spatial coverage, limited thematic detail in the number of wetlands it identifies, in that it was produced using variable methods and model inputs, which has resulted in variable quality. And its production is now quite dated, since the imagery used to produce it was from 1998 to about 2015. So as a result, there is quite a motivation to update this inventory. In the ABMI and the DUC, our organizations have been at the forefront in developing technology for wetland mapping, with a particular focus on inventory enhancement. So for example, what you see here is a relatively recent demonstration of machine learning for wetland mapping at large scales, which highlights the advantages of using consistent approaches and temporally aligned satellite imagery. However, this ABMI inventory is also limited to only the 5 major wetland classes in Alberta, and its relatively moderate resolution is less applicable in southern regions where wetlands are quite small and very dynamic. But with all that said, there is a clear need for an updated provincial wetland inventory. And as a result of this need, the Government of Alberta developed, in collaboration with many stakeholders, a set of standards and guidelines for wetland mapping across the province. So these standards identify the minimum specifications for inventory production across Alberta, and that includes, for example, detail, accuracy, and minimum sizes, with an overall goal with an intention goal to support consistency, improve data quality, and have support for wetland policy, monitoring, and planning around wetlands. But as you will see across my presentation, these standards are really what provided guidance for the pilots that I'll be describing. Now, in terms of the inventory standards, the Government of Alberta has identified that mapping should correspond to the Alberta Wetland Classification System, whereby in the Prairie Parkland region, mapping should be to the class detail. So that's the middle dark blue labels on the image. Whereas in the Boreal Foothills region, mapping should be to the form detail, which are the lighter blue labels at the bottom of the image. For minimum accuracies, these should be 90% at the general wetland upland split, 80% at the class detail, and 70% at the form detail, with minimum mapping units, or minimum wetland size detection, being 0.04 hectares in the Prairie Parkland region and a little bit larger, so 0.9 hectares in the Boreal Foothills region. And in response to these provincial guidelines, the Government of Alberta contracted DUC and our organization, the ABMI, to collaboratively develop innovative methods aimed at meeting these minimum mapping standards. So for this project, the work was led by the GOA and their Environment and Protected Areas Technical Committee, and the work was funded through the Wetland Replacement Fund. And our joint organization, so ABMI and DUC, we work quite closely in collaboration and in guidance by our established MOU. And with this work, we acted as equal partners and contributors by leveraging our combined expertise in mapping and wetlands. But within this project, our designated project teams set out to meet 3 specific objectives. So the first one is we wanted to evaluate new and available remote sensing and AI technologies for meeting this set of GOA mapping standards. 2 is we wanted to develop pilots with associated methods to address this first objective. And then 3, we wanted to use the findings from our work to provide a set of technical recommendations for provincial inventory updates. And for this work, we developed our methods within 4 pilot areas across the province. So that was 2 in the Boreal Foothills region and 2 in the parkland grassland region. Now, these pilots were carefully selected with consideration of available remote sensing data, in particular in high resolution lidar imagery, which was quite important for meeting accuracy standards, but also available field validation data that both our organizations had access to. But with that, let's move on to more of a detailed review of the pilot methods and how our teams accomplished wetland mapping within these collective study areas. So the methods for the project were developed based on recent advancements found within literature and best practices in AI and machine learning modeling. So this collectively resulted in a data-driven approach that combined multiple sources of satellite and airborne remote sensing data with extensive plot and field validation data so that we can model and predict wetland classes and forms and their spatial extents within each pilot region. And additionally, as you'll see at the far right there, a very important piece of this project was model accuracy assessments, which were used to inform our recommendations for methods implementation. Now, in terms of inputs to our AI models, our methodology relied on multiple remote sensing data sets collected by various satellite imaging systems. So this included sources of optical and multispectral imagery, which are quite sensitive to vegetation condition, composition, and health, radar imagery, which is sensitive to moisture and water properties, and terrain imagery, which highlights topographical features and landscape gradients. But quite critically, our satellite imagery, we also complemented it with airborne LiDAR data, which is an acronym for light detection and ranging. So LiDAR is a high-resolution source of topographical data, and it provides 3D imaging of the Earth's surface and allows for the calculation of numerous features related to wetlands, so for example, such as landscape position or ruggedness, flatness, wetness, or also vegetation components such as the height of canopies. But without this LiDAR data, which was delivered by several partners listed on the bottom left of the slide there, this project really would have not been as successful as it was. So in terms of training our AI models for this work, in all pilots, we had used an extensive repository of plot data, which we also refer to as photoplots. So these spatially continuous photoplots covered areas of about 3 by 7 kilometers in our boreal pilots and about 5 by 5 kilometers in our southern prairie parkland grassland pilots. And each of these photoplots, they were produced from high resolution imagery, and the result was they were able to identify wetlands in their full spatial extents, which allowed us for model development and AI training. So as illustrated in our project objectives, the evaluation and use of AI within this work was quite imperative to addressing the standards for wetland mapping. So for image classification of wetlands, we assessed 2 key types of AI modeling. First was machine learning, which is a subset of AI that's founded in statistical analysis for pattern recognition. And the second was deep learning, which is a subset of machine learning, whereby these models are inspired by the structure and complexity of the brain. However, it is quite important to note that model complexity does not always mean better results, but rather mapping performance often depends on a number of factors, such as data inputs or the task itself, or just the ability to generalize. So it's quite valuable to understand the general advantages and limitations of AI types, hence why we assessed both approaches in this project. So for example, it's quite a prevailing understanding that deep learning models have very high accuracy potentials, but these models need a lot of compute and large training data requirements. In contrast, machine learning models can typically produce good predictive results with less training data, but their high-end potential is somewhat more limited. So while this poses some challenges relative to achieving higher accuracies, it does suggest that machine learning may be more fitting for rare class detection or in cases where resources and plots are more limited, whereas deep learning may be more valuable for mapping majority classes or in cases where trained data is less restrictive. But the way these AI models process training data, it also has major implications on not just accuracies, but also what the output maps and predictions look like. So for example, with machine learning models, as you can see on the left, they process samples as individual or single pixels one at a time, and they therefore don't consider the pixels surrounding an individual sample. Now, the results of these models are they're more granular and variable, which can be or have both its pros and cons. In contrast, deep learning models, as you can see on the right, they are patch-based, and therefore they consider this or the neighboring pixels when learning. And this results in edge and texture detection, and typically in smoother, more generalized maps that are of higher accuracy, but can often sacrifice more minor or granular details. Now, there are ways to mitigate these challenges with each AI modeling type. So for example, with our machine learning models, we address the challenge of trying to achieve more stable and less variable predictions by using a strategy of multiple model runs trained on different sample point collections, and then summarizing model inputs into a single most occurring majority map. And this group technique is something that represents a best practice approach in machine learning modeling. And with our deep learning models, we know that since they are often considered data starved or in need of lots of trained data, what we did is we implemented quite aggressive data augmentation techniques in which trained data is artificially expanded by performing things such as patch flipping and rotating, which can result in substantially larger and more diverse training sets for our models. And again, similar to our machine learning approaches, this is quite a widely accepted and best practice in AI prediction modeling with neural networks. But for the field validation data itself, our collective organizations deployed teams with the goals of collecting multiple sources of ground and helicopter-based validation data. So in our northern boreal foothills pilots, this resulted in several hundred survey samples across each pilot from air and ground-based methods. But helicopters in particular, they were quite necessary in these regions since ground access is highly limited, for example, from thick forest and vegetation cover, which these conditions make, for example, many wetlands otherwise very inaccessible. But nevertheless, where we could gain access, ground plots with critical soils and water information was used to complement our helicopter-based validation data set. And in the southern grassland parkland pilots, our validation followed a slightly different approach, whereby we relied solely on dense ground-based sampling of full parcels over 2 years, rather than using helicopter surveys. So this approach was, of course, more feasible due to limited forest cover and easier physical access, but these validation efforts were more challenged by land ownership and access permissions. Nevertheless, the approach itself, though, of this full parcel ground truthing, it did provide our modeling teams with a strong validation data set for AI model performance and evaluation. And in informing the in-field validation efforts was a set of comprehensive protocols that we developed, which detail methods for specifically typing wetlands according to the Alberta Wetland Classification Schema. So as you can see from these visual illustrations, these protocols provided guidance on plot setups, instrument installation, data tracking, and other important validation setup criteria to ensure that this ground data collected was highly accurate and relevant for wetland mapping and accuracy assessment tasks, but both for within these pilot projects and also for any forthcoming mapping projects. Now, onto some pilot results and the implications of the methods that I just described. So first, let's take a look at the results of the boreal foothills pilots. So what you see here are a set of radar plots, which identify the benchmark accuracy target that's set out in blue, and that's what our models are trying to reach. And then what you see is the actual accuracy results for each model configuration, which is displayed in red. So at the more general wetland class detail, which includes only 5 major wetland classes, what we found was that 2 particular deep learning configurations achieved the best performances and reached the minimum provincial accuracy standard of 80%. Or in other words, these models reached that blue target line. So these models included a highest 82% accuracy in our Boreal 1 pilot, and then 87% accuracy in the Boreal 2 pilot, again, which was achieved with a deep learning model configuration. And following this, we then tested similar model configurations at the more detailed wetland form level, which includes mapping of 13 wetland forms. And what we found here was that a certain machine learning approach generated the highest accuracies while also meeting the benchmark provincial standard of 70%, or again, that blue line. And this overall result aligns with my earlier introduction and description and hypothesis of AI technologies, in that deep learning is typically more capable when we have fewer, more broader classes, while machine learning can be more effective when there are more rare thematic classes, but limited training data per class. And now what you see here are the final inventories of Boreal 1 and Boreal 2 pilots, using the predictions from our best AI models that met those provincial mapping standards. And what we see here is that wetlands very much dominate almost and even above about half of these pilot areas. And certain wetland forms like shrub and tree fens and conifer swamps, they were quite spatially extensive across these pilots. And when we take a closer look and compare our model outputs side by side, we can see that the predictions very much reflect the AI technologies and their learning capabilities. So for example, in the middle row, we see that the machine learning predictions are far more granular and variable, whereas in contrast, the bottom row, used to map wetlands with deep learning, shows more of a smoother generalized output. Now, while each of these have their pros and cons, what we can conclude here is that there's actually an opportunity to collect generalized ecosystem extent information from deep learning models, whereas machine learning models can be complementary for more mapping of fine scale variable vegetation community details. But one advantage we did find in both our AI approaches that I would like to note was the effectiveness of mapping wetlands in fire disturbed areas, which is typically a very challenging task since fire causes drastic changes in spectral reflectance of land covers. So by providing our AI models with training data of wetlands within those areas, we found that our AI models could preserve the spatial patterns of wetlands and accurately predict their extent regardless of disturbance, which is a very important finding since, again, wildfires are extensive and naturally recurring in Alberta's boreal biome. But now let's take a look at the prairie parkland pilot results, where we actually evaluated a broader range of model configurations, which reflects really that these regions were more in the earlier stages of AI R&D. So unlike our boreal pilots, though, our assessments focus directly on wetland form detail mapping and not class detail, since overall wetland diversity is quite low in southern Alberta. So what we found in our results was our deep learning models could achieve very high overall accuracies, so far exceeding the 70% benchmark target you see with that blue line. And with a certain deep learning configuration, our models could actually reach 93 and 94% overall accuracy, which is quite impressive. But despite the strong overall performance, I should note that our deep learning models quite struggle to reliably map certain wetland forms. So for example, peatlands, particularly since there was limited training data and occurrence for these various ecosystems. In contrast, our machine learning models, despite having lower overall accuracies, could more consistently capture these rare wetland systems across each pipeline. Now, when we take a look at the overall inventories of these pilots, which were produced using our best AI models, we can see that these regions are largely comprised of open water and inundated marsh ecosystems, which is highly reflective of the prairie pothole region in southern Alberta. On the other hand, peatlands and swamps are far more minimal, and in several of these, or one of these pilots, even absent in one of these regions. But when we take a closer look at each AI approach, what we see is that despite the accuracy differences, that both approaches produce very qualitatively accurate wetland predictions. And even in our parkland pilot, which had more instances of rare fens and swamps, we still see quite good predictions. But in many cases, our visual differentiation against validation truth labels, which you see on the left, was quite difficult, to differentiate between our predictions and the truth labels, even with our deep learning, which was a little bit less capable with minor form wetland detection. And in comparison, when we look more closely at the more southern grassland pilot, we see that since marshes form much of the dominant wetland extent, that our deep learning models perform quite well over machine learning, since there's less diversity in these regions and there's more of a majority form dominance. But regardless, when both AI approaches are visually compared against our labels, which again are seen in that left panel, we can see that the predictions match very closely to truth for both deep learning and machine learning. But regardless of pilot, a prevailing challenge of mapping prairie pothole wetlands is that they have extreme spatial and temporal variability, which really is a result of their characteristic flooding and drying regimes. So as you can see on the right, when tracked over time, we can see that these wetlands differ in their extent depending on season and date, which makes satellite imagery acquisition and ground truthing timing quite critical for mapping and model assessment in this biome. But even with that in mind, our AI models, both of them were quite capable in achieving the standards set out for prairie parkland mapping. And once again, visually, when we look more closely at the challenge of mapping more minor or rare wetland forms, such as peatlands and marshes that have been tilled, what we find is that our machine learning models are really the only approach that can capably map these wetlands, which is quite evident when we assess against more conventional modeling approaches, like what you see on the left, and even more advanced deep learning approaches, which you can see in the middle tile, which again generally lose some of that minor information due to the way they process input data. But with all that, let's go over some summary takeaway messages that our project teams have compiled based on these qualitative and quantitative findings from these wetland mapping pilots. So a key objective of our work and our project was to come up with a list of technical recommendations for government to consider for new wetland inventory development in the province of Alberta. Based on our findings, our team suggests that first, that lidar imagery is quite critical for inventory development, but of varying specifications due to vegetation cover. That two, aerial imagery is very important for the development of plots. That three, that plots, or what we call photo plots, are very necessary for model training. That four, that satellite imagery is very key for scaling predictions, but that higher resolutions are needed in the southern regions where wetlands are much smaller, and more moderate resolutions work well in the boreal foothills region. And lastly, that our modeling approaches would benefit from a combined machine learning and deep learning approach, whereby the benefits of each AI type is used in a complementary fashion. So for example, that might be being able to map the extent of wetlands with deep learning models, and then use machine learning for fine form classification of vegetation communities. And when we track back to our project objectives, what we found was that, one, we were able to evaluate several remote sensing data sources and AI technologies, such as machine learning and deep learning for wetland mapping in Alberta. That two, we were able to develop pilots and associated processing pipelines to address the first objective. And three, our results have led to a set of technical recommendations that I just described, which we expect will inform future provincial wetland inventory updates across all of Alberta. And with that, that concludes my presentation. I'd just like to say, again, thank you to the project teams and then everyone today who joined the webinar. Much appreciated. But with that, I will stop my presentation and pass it over to Sonia, and then we can do some a question period. So thanks, everyone.